Assalamualaikum warahmatullahi wabarakatuh. We are from Group 1 B7. My name is Muhammad Lukman Arif.
And I'm Adil Abdul Aziz.
I'm Siti Nur Hakimah binti Rozi.
I'm Nurul Fateh. I'm Sharifah Aisyah Shamira. I'm Faridah Hani.
Today, we are presenting to you about the molecular geometry of covalently bonded atoms. Okay, enjoy our video.
We are here to present about CH2O, or generally known as formaldehyde. CH2O has this kind of Lewis structure because it has one unpaired electron, so it will share another pair of electrons from O2 and form double bond here. So this is the best Lewis structure as it has the formal charge minimized or mendekat or yeah, that's it.
Okay, as we know, CH2 has this structure. The presence of two pairs of lone pairs will repel 2H and form trigonal planar shape. The angle will be 120 degree as 360 divided by 3. So this is our model, and you clearly see that this is a pi bond, this is sigma bond, and sigma bond. The pink color is a C, the blue color is O, and the yellow color is hydrogen. Okay, the polarity is oxygen is the most electronegative than other two elements. So the polarity is always from del positive, which is H, to del negative, the most electronegative, which is oxygen. So the polarity is pointing upward, which is the net dipole moment is not equal to 0, and this is the polar molecule.
Okay, how to perform hybridization on CH2O? Okay, we need to hybridize C as the central atom. So carbon has 4 electrons as it is from 4A group, and then this is the ground state. It consists of 2s orbital and 2p orbital. How we can satisfy the electron, since it has only 2 electrons, we need to excite it to the or we call it promotional state. We take one electron from s orbital, go to the p orbital. So it will form this kind of partially orbital electron. So from this we can conclude that hybridization for CH2O is sp2 and it has one unhybridized electron
From free group, and this is will form pi bond with O. As we know, formaldehyde has C, O, and 2H. C will form sigma bond with 2H, and it also will form one sigma bond with O. C and O will form one pi bond, and this is O, and it has 2 lone pair. This is the orbital overlapping in formaldehyde molecule. Thank you.
This is boron tribromide. Okay, first, I will tell about Lewis structure for boron tribromide. First, we draw B at the center as it was less electronegativity than bromide. Then we draw 3 bromide because it has 3, and we draw its valence electron. And why boron doesn't have valence electron? Because boron valence electron for borons, it have formed a bonding pair between boron and bromide atom. And the formal charge for bromide and boron was 0. Okay, this was the best pair for boron tribromide. The shape for this, the geometrical shape for this molecule is trigonal planar. As we can see in our model, it forms 120 degree for each angle. So this is our model. The white color is boron, the orange color is bromide. It has same shape as this principle. So what I have drawn in front of it. Okay, this molecule was non-polar molecule because the net dipole moment was 0 as the dipole moment will cancel out each other and we got 0. Okay, this was the orbital diagram for boron tribromide. First, we determine its steric number. It have 3 because they have 3 sigma bond, and sp2 because the spp, so it have 2p. And this is ground state for boron only, boron atom, which is 2 electron at s orbital and 1 electron at p orbital. When it have in excited state, it will promote 1 electron from s to p orbital, and then in hybridized state, it will form this, which is sp2, spp, have 2p, and this was the overlapping orbital overlapping for boron tribromide. Okay. The center is a boron, and these 3 like double shape is bromide. So this was the sigma bond, which is head to head, and they share electron. This electron that they both atoms share. That's all from me. Thank you.
So, right now I'm going to present about hydrogen cyanide, HCN. This is the Lewis structure for HCN. This is the best Lewis structure for HCN as the formal charge is 0, 0, and 0. This is a sigma bond, this is sigma bond, and this 2 is pi bond. And this is the Vesper for HCN. The shape for geometry, the geometry shape for HCN is linear and the angle is 180 degrees. HCN is a polar molecule as the net dipole moment is not equal to 0. The steric number for HCN is 2 because steric number is the total of sigma bond plus lone pair. So as there is 2 sigma bond here, so the steric number is 2. And the hybridization for HCN is sp. So this is our model for HCN. This yellow color present for H, this green one is C, and this pink one is N. Here is a covalent bond, and here is triple bond. This is the pi bond, sigma bond, and this is also sigma bond. So this is the ground state for carbon atom, 2s2, 2p2, and this is the excited state. 1 electron from s orbital is promoted to p orbital, and this is the hybridized state for carbon. 2 electron is hybridized and another 2 electron is unhybridized, as it will form pi bond. And this is the overlapping diagram for HCN. This is C, this is N, and this is H. This is the sigma bond, and this is the lone pair. This is the pi bond, and this is the pi bond. That's all from me, thank you.
Hi, we will explain about SeCl5-, which is selenium pentachloride anions. This compound receives an electron from other element, which is why this compound has a negative charge of 1. And when we calculate the formal charges for each atom in this compound, for Se, for the selenium, you will get -1, and for the Cl, you get the 0. So, the total of the formal charges is -1. That makes sense when this polyatomic ion has a negative charge of 1. And then, these formal charges are the least. So that's why we get the best Lewis dot structure for this compound. And the as we look for the molecular geometry for this compound, we will get, for the set of electrons, it sits as it sits. So we know it is octahedrite. But when we look at the bond, we will see the bond is 5 bonding pairs and 1 lone pairs. So it makes the shape of the molecular geometry is square pyramidal. And then for the angle of the bond in this molecule, in this ion, in this polyatomic ion, the angle is less than 90 degrees. Why is this so? Because this lone pair will take more angle than this bond of Cl does. So it means that it will push away, it will repel away this Cl atom, and it makes this between the angle between this bond and this bond is less than 90.
Now we look at the polarity of the molecule of the compound. To determine the polarity of a compound, first we have to look at the net dipole moment of the compound. As we see here, the net dipole moment of this particular compound is not equal to 0, which means it is polar. How do we know this? First, we draw the dipole arrows. Dipole arrows are drawn from partially positive to partially negative atom. In this case, Se is the partially positive atom and Cn is the partially negative atom. So the arrow moves from Se to Cn. In this case, these two arrows will result in a dipole moment in this direction. Same goes for this side, and these two will cancel each other out. But in this particular Cl, this dipole moment does not cancel, which means the mu is not equal to 0, which is why the compound is polar. And now I'll talk about the hybridization of the SeCl5-. To determine the hybridization, the type of hybridization, first we have to look at the central atom. In this case, it is Se. We look at the ground state of Se, the ground state partial orbital diagram of Se, which is 4s2 4p5. And then we look at the excited state. In this state, 2 electrons from the 4p orbital is promoted to the 4d orbitals. And the energy levels between all the orbitals become the same, which results in the hybridized orbital of sp3d2. We can also initially determine the type of hybridized orbital by using steric numbers. Steric numbers is basically the sum of sigma bonds and lone pairs. In this case, there are 5 sigma bonds and 1 lone pair, which equals to the steric number of 6. And that's it. And from that we can get the type of hybridization sp3d2. And now we look at the orbital overlap of the compound. This black one here is the sp3d2 diagram, and sp3d2 orbital, while these blue ones are the 3p orbitals of chlorine. As we can see here, 5 singly occupied sp3d2 orbitals of Se is overlapped with 5 3p orbitals of Cl. And so there's one lone pair here.
Okay, that's all.